Next up, we're going to talk about the determinant of a general n-by-n matrix. So big definition, but the best way to master this is just by going over some examples. So how do you compute the determinant of a general n-by-n matrix? Well, the trick here is you pick either a row or a column. It does not actually matter which one you choose, but you just choose one row or one column. If you choose a row, then the determinant of A is along that row. So here the entries on the ith row is A, I1, AI2, AI3, AI4, all the way up to AIN. And then what you do is you multiply all the entries by their corresponding cofactors, C1, CI1, CI2, CI3, CI4. So you multiply the entry with their cofactors, you sum up, and then that's your determinant. So you can do this along a row, or you can do this along a column. So if you pick the J column, the entries are A1J, A2J, A3J, ANJ, and you multiply by their corresponding cofactors, C1J, C2J, C3J, and CNJ, and that will give you an equivalent way to compute the determinant. So you pick a row or you pick a column, and then you just multiply the entries by their cofactors. So because you're using the entries in the computation of the determinant, if you pick a row or a column with a lot of zeros, and this is a very important remark here, then of course this computation will simplify greatly, because if you have an entry times its cofactor and the entry is 0, then you don't even have to compute the corresponding cofactor. So if possible, to simplify the computation, always choose a row or a column with as many zeros as possible, or, and we'll see this later, you can actually use elimination to create zeros and then compute the determinant. So let's do some examples. So we have, for the first one, so we have a 3x3 matrix. So the first thing you should do, so this remark is going to be used everywhere, choose a row or a column with as many as zeros as possible, if possible. So here I'm going to go and choose row 3 because I see there's a 0 there. So once I've chosen my row, my column, one thing I like to do is just do my sign expansion. I know the top left corner is always a plus, so I have a plus in the top left, and then I just go down to my third row. So by alternating signs, I have plus, minus, plus, minus, plus. So I see my 7, sorry, my minus 7 is at a plus position, my 0 is at a minus position, and my 3 is at a plus position. So now I will expand along the third row. So my determinant of A is going to be minus 7. And there's a plus. It's a bit redundant here, but I just want to stress the fact that I'm thinking about it. So it's plus minus 7 times the determinant. So at minus 7, if I remove, so you need to remove row 3 and column 1, because this is where the minus 7 is, and you're going to get this sub 2x2 matrix. You're going to get minus 5, 4, minus 3, minus 1. Then there's minus 0 times something, but I don't care. Skip every 0, and then I just move to the next non-zero entry. In this case, it's plus 3. So 3 is my entry times the determinant. So at 3, I need to remove row 3 still, and column 3 to get my submatrix. Submatrix you're going to get there if you remove row 3 and column 3 is 1 minus 5 2 minus 3. And now the only thing you have left to do is to compute 2x2 determinant. So I'll do my fish formula, and then I'll be done. So I get 7, open a bracket, minus 5 times minus 1 minus 4 times minus 3 plus 3, open a bracket, 1 times minus 3 minus 5 times 2. Oops, just forgot the minus in front of the 7 here, sorry. So you're going to get minus 7 times, so you have 5 plus 12, which is 17, plus 3, and then you have minus 3 plus 10, so minus 3 plus 10, that's minus 3 plus 10, that's 7, and then if you do the math, you're going to get minus 98. So the determinant of A is minus 98. And I just want to make a very important remark here with where are the marks distributed. So if you have a question like this to compute a determinant, half of the mark will be for that row of computation. This is the most important part of the computation. If you can show me that you know how to expand along a row or a column, then I'll be very, very happy about it, and you're going to get most of the mark. Then the rest is really just be careful, don't make any sign mistakes. It's easy to make a mistake there, but that line here of the computation really shows if you understand or not, like the ideas behind computing a determinant. Next, let's compute the determinant of I4. So we want to compute the determinant of the n by n matrix 1 0 0 0 0 1 0 0 0 0 1. So this at the same time reviews notation of identity matrix. So here I'm just going to use the first row to expand, and of course the 1 is at a plus position. So when I'm expanding, I'm getting 1 or plus 1, so I like to put the plus just to really stress it, times the determinant of the minor. So, and here because there's only one, it's actually not too bad. I can actually just circle the sub 3 by 3 matrix when I'm expanding around the 1 at 1 1. So times the determinant of 1 0 0 0 1 0. So here I remove row 1 and column 1, and then it's a rinse and repeat process. So we have a new matrix. It's a 3 by 3. I'm going to choose again the first row. So I'm going to get, if I continue down, I'm going to get 1 times 1. Again, here the 1 is at a plus position. I'm not going to write it down, but just for you. So here determinant of, and of course the submatrix there. I can circle it because there's not much going on with this example. So that's my submatrix times the determinant of the identity I2. Now I do my fish thing. So my fishy product, I get 1 minus 0, so you're just getting in the end 1 times 1 times 1, which is 1. As a remark here, if you compute the determinant of any identity matrix of any size, you're always going to get 1. Always. Next example, so we're going to choose, for matrix A here, we're going to choose column 3 because there's 2 zeros in it. So if you do the expansion, you're going to get that the determinant of A is, so if you look at the alternating signs, we have plus, minus, plus, minus, plus, minus. So 1 is at a plus position. So you write your plus. I'll put the 1 in red so that you see where it comes from, times the determinant. So the sum matrix for 1, so I use red here to remove row 1 and column 3. So the sum matrix is going to be 2 minus 2, 6, 1 minus 6, minus 9, and 3 minus 3, 4. and then you're skipping over the zeros. You're going to get a minus, because minus 2 is at a minus position. Use purple here for the minus 2. And then the submatrix for minus 2, if you remove row 4 and column 3, so the purple lines here, so the determinant of, so the submatrix you're going to get is the following, so minus 4, 3, 5, so I'm just removing the purple lines, so you're going to get 2, minus 2, 6, and 1, minus 6, minus 9. Alright, next I'm going to just choose the first row for each of them because none of them have zeros, so you're really stuck. I'm going to do the sign expansion, so plus, minus, plus, plus, minus, plus. So you just have to be careful. This is very boring, but it's not too difficult. So you have 1 times the determinant. Sorry. So if I expand now the determinant, so 1 times, open a big fat bracket, 2 times the determinant. If you remove row 1, column 1, you're going to leave behind minus 6, minus 9, minus 3, and 4, minus 2. So remember the minus is because minus 2 is at a minus position, so determinant of, so the submatrix here, moving row 1 and column 2, you're going to get 1, minus 9, 3, and 4. Just be careful. And then plus 6, so 6 is at plus position. Determinant of the minor there, so the submatrix, 1, minus 6, 3, minus 3. So plus, so the minus 1, minus 2 is going to give me plus 2. Open a fat bracket, so I'm on the second determinant now. So yes, minus 4. If you move row 1, column 1, the submatrix is minus 2, 6, minus 6, minus 9, minus, so the 3 is at a minus position, so 3 times the determinant, so you're moving row 1, column 2, so you're getting 2, 6, 1, minus 9, and then plus 5, so 5 is at a plus position, determinant of the submatrix here, removing row 1, column 3, so 2, minus 2, 1, minus 6. And now you have to compute those nice 6 2x2 determinants. It's full of fun. So now we only have to compute 6 mini fishes. So even if you start with a 4x4, these computations, they always end up with the computation of 2x2 determinants. And now if you do your determinant computations, you're going to get, so the first one is going to give you minus 51. The second one is giving you 31. Third one is 15. This one is 54. Minus 24. And minus 10. So if you rewrite this as one computation, you're going to get 1. Open a big bracket. 2 times minus 51 plus 2 times 31 plus 6 times 15 plus 2 times, open a big fat bracket, minus 4 times 54 minus 3 times minus 24 and plus 5 times minus 10. And then if you compute all of this, you're going to get a big minus 338 because I already baked that answer earlier. And that's it.